Welcome back. I want to talk about a new topic today, namely this one, combustion. So, combustion is a type of reaction, and what we're going to be doing for the next couple of weeks, including during this blow things up week, is learning about different types of reactions and how to predict them. So, for instance, let's say I want to predict a reaction. I don't need to write this down, kind of like this one. You'll notice there's something pretty different about that reaction and things we've worked at, namely, where are the products? And what we're going to be learning how to do over these next couple of weeks, including with a lot of demonstrations, is say, you know what, I recognize this. This is a combustion reaction. I know exactly how to predict that. And so what you're going to be asked to do is say, look, I know what kind of reaction this is. Not only do I know what kind of reaction this is, I know what this makes. This makes carbon dioxide, and this makes water. And you're going to be asked to actually pull that out of your own mind and say, you know what, I know how to do this. I can make that prediction to show that it happens. So how do you know you have a combustion reaction? How do you know that it's going to make these things? That's the kind of questions we're going to begin asking. We'll be exploring more and more for the next couple of days. So on your little note sheet there, it says all combustion reactions contain something as a reactant. And this is, honest to God, the easiest part of this. Okay? Combustion reactions are really easy to identify because they have one thing in common. Combustion reactions have oxygen as a reactant. So as soon as you see oxygen by itself as a reactant, I'm talking about O2 diatomic oxygen free from the atmosphere, that kind of oxygen, you know you have a combustion reaction. End of story. If you see oxygen, it's combustion, at least in one form. There could be the second reaction happening in addition that we'll talk about later. So a combustion reaction is really easy to predict. As a matter of fact, combustion reactions are probably the easiest to predict because they always make the same two products. More about that in a second. But for right now, if I give you a list of reactions, which are going to appear here in just a second, you're going to see picking out is it a combustion reaction is pretty easy. So let's take a look at these reactions here that just appeared. This one isn't combustion, even though it has oxygen as a reactant, because it's bound up with OH, this isn't combustion. Here, again, even though the oxygen is all tied up in this nitrate group, that doesn't matter. I'm looking for oxygen by itself. So this is a different class of reaction too, not combustion. On the other hand, I see oxygen here, so that better be combustion. And of course, the bottom one, again, because it's tied to nitrate, no combustion. Easy. All we need to do is look to the left side of the arrow, to the reactant side, and say, is oxygen present? And if oxygen is present, I've got a combustion reaction. All right, so let's talk about one family of combustion reactions, which is going to be involving chemicals of this form, of a C something H something. Right, CXHY, and these are really common in nature. Actually, we could even throw some more stuff onto the end of that and still have them fit the same categories, but we're going to keep it easy for this class. So when you have a carbon bound to hydrogen in any ratio, just carbon and hydrogen together in some form, we have a special name for it. That name is a hydrocarbon, which makes sense. It's a hydrocarbon. Okay, so hydrocarbons are very common in chemistry. Hydrocarbons are things like butane. This is some ratio of carbon-hydrogen that reacts to burn. Butane's in every lighter. You have, well, propane, which you're familiar with on my grill. You have things like methane, which is what you burn in a Bunsen burner. You have things like octane and heptane, which make your gasoline work. And lots of other things. I'm not going to make you learn how to name hydrocarbons. That's awful. All I want you to do is recognize that you have hydrocarbons as a reactant. And when you have a hydrocarbon reactant and oxygen, it always makes the same two products. Those two products are carbon dioxide and water. So when you burn things in your car, ostensibly, if it's working right, it should only make carbon dioxide and water, which outside of greenhouse effects really are pretty safe. On the other hand, combustion never is as easy as it seems, and you always get some side products. So whenever you're burning one of these things, you're always going to get the same two things. And those things are really common. So if I know that a combustion reaction has oxygen and that hydrocarbons can combust and make these two things, I can write like a generic formula for what's going on. Okay, that's easy. So I have my hydrocarbon, CXHY. I don't care if that's CH4, C2H10, C3H8. I don't know what it's going to be. I just know that it's going to be an X and a Y. It's going to be some two numbers there, right? And they're going to burn in the presence of oxygen. Easy enough. And it always makes these two things. So no matter what, as soon as I see that CXHY business, I know I'm going to write CO2 and H2O, which makes this really easy. If I need to make a prediction about what's going to happen, and I see a hydrocarbon, I'm done. Every single time it looks the same. This is our generic formula. It's probably the easiest of the reactions to complete. So let's look at a couple of these examples. Specifically on your worksheet, I have two here, which look like this. And those are methane and heptane, and they're burning in the presence of oxygen. Now, looking at these, it's really easy to figure out what's going to happen, because look, I see oxygen, okay, cool, it's a combustion reaction, check, done. And not only that, I see that they're hydrocarbons, because they've got some number of carbons and some number of hydrogens. So predicting what's going to happen here is as easy as looking back at our generic equation saying, wait a minute, I know this. It could be carbon dioxide and oxygen, water. Unfortunately, I also ask you to balance them. Okay, sometimes balancing them is pretty easy. I have one carbon, ooh, two hydrogens here. Okay, so I've got 2 oxygens plus 2 more oxygens. Easy. We've done that reaction a lot of times. Be careful, because the oxygen is split up, right? Because there's oxygen in both products, and this one's a 1 and this one's a 2, this bites students in the butt. And balancing these can get kind of hard pretty fast. Okay, lots of students will be like, here I put a 7. And please do start with the carbon, it's easy. My suggestion for balancing combustion reactions is to go in alphabetical order. C, then H, then O. Again, so you might even write that down on the side of your notes. Do alphabetical order for balancing, and your life will be easier. And if it doesn't work, you generally end up multiplying by 2. So this is a reaction where you would need to multiply by 2. I can know that just looking at it. Eventually you do enough of these. So kind of to save ourselves some time here, I'm going to throw a 2 in front. And if you missed it and you're like, I'm stuck, I can't balance it, generally throwing a 2 in front of the most complicated term fixes things. So I need 14 carbons, right? 2 times 7. So I can only get carbons from here, so that's easy. I said to do alphabetical order, so I need to do H next. Let's see, I've got 32 of these hydrogens. And I can get 2 of them each time, so that's going to be a 16 here. Neat. Now I need to do the oxygens. And luckily I have oxygen free. As long as this comes out to an even number, I'm golden. So 14 times 2 is 28. 28 plus another 16 is 44. Which means I need 22 of these oxygens, which is a huge number. And you see that balancing these can get a little messy. And that's okay. But do be aware that it pretty much will work if you go in alphabetical order. And I will tell you the carbon term, this hydrocarbon will always have a coefficient of either 1 or 2. You'll never need to go above 1 or 2 on the CXHY term. E. There's also a second kind of combustion that doesn't involve hydrocarbons. Hydrocarbons are nice because they always have the same products. The other option is a metal reacting with oxygen. So those kinds of things are going to have a generic formula that looks something like this, which is an elemental metal and oxygen reacting to make the, well, metal oxide. And this is kind of a heady definition. I think it makes a lot more sense if we just look at a couple examples. So those are specifically the combustion of iron and magnesium. So let's look at magnesium first, the bottom example, because I actually think that one makes more sense to me. So magnesium, it's in the second column of the periodic table. It forms a +2 charge if you look at your ion sheet. There'll be an ion sheet in the back of your homework today. And oxygen always forms the same charge, which is a -2 charge. So when I'm predicting what's going to happen here, I'm going to have to look at the ion sheet and figure out how to cancel pluses and minuses. So what I like to do is underneath the thing I'm doing, I actually like to remind myself what these things do. So I get Mg2 plus and O2 minus, and that means these things cancel out smoothly. I'm just trying to get M, G, and O. Great. Right, because Mg is a +2 and O is a 2 minus. But what happens in this tube, Mr. Nendick, right? Because it shouldn't be MgO2? Well, no. Just like before when we learned how to do ionic synthesis, we got to balance the equation using coefficients. So if I have 2 oxygens here, the easiest thing to do is just throw a 2 out in front. So again, your charges have to cancel. So on your ion sheet, you might notice that Fe makes the +3 species, right? So when you get like Fe3 plus and O2 minus. Well, that's great, but that doesn't mean anything to me unless I actually cancel those things out. So I erase the signs here, and I bring them down to their opposite sides, and I get Fe2O3, which hopefully is a familiar chemical to you. That's obviously rust, red iron rust, the thing that makes your car not as nice. But for a second, that's actually really weird. After all, I'm telling you that this is a combustion reaction, and this is red iron rust. So what I'm saying is, when your car is rusting, it's combusting, which doesn't make sense, but to a chemist, that's exactly what it means. Not all combustion is a really fast fire. Some combustion is something like rusting. It's slow. It's anything reacting with oxygen. So that's the thing that's kind of unique to Earth. Combustion is kind of a prerequisite to living organisms, for instance. I am combusting right now, which is kind of confusing insofar as I'm alive and I'm converting oxygen to carbon dioxide, right, and water. When I take an air and respirate, ultimately that's a combustion reaction. That can twist people's mind, but the predictions are easy, right? Either I'm making a metal oxide using the ion sheet, or making a hydrocarbon that turns to carbon dioxide and water. So predicting these is easy. So again, kind of in summary, you're going to look for these O2s. You're going to decide, is it a metal or a hydrocarbon? If it's a hydrocarbon, you know exactly what to do. If it's a metal, you're going to use the ion sheet and make the oxygen in the -2 form combine and then balance out the equation. Now, of course, up here I didn't actually finish this. I've got to balance it, but that's not too bad after all. There we go. And we're good. So what I'm going to ask you to do for, let's see, today's Monday, so Tuesday, Wednesday. For Wednesday is to do the back side of this sheet, which has a little bit of these things to practice. And don't get me wrong, we'll spend the first 5 or 10 minutes on Monday going through these things as an example. I'm not going to sit here and expect you to know this perfectly from the video, but that's where I want to finish for today.